Hello and welcome back. In a previous video, we discussed capacitors, and in that video, we derived the formula for the strength of the electric field between the plates of a capacitor. In this video, I want to talk a little bit more about capacitors, and in particular, I want to derive a formula for the voltage difference across a capacitor, as well as a formula for the total energy that's stored inside a capacitor. Recall that a capacitor consists of two oppositely charged plates that are placed next to each other. Additionally, remember that the electric field inside a parallel plate capacitor points from the positively charged plate towards the negatively charged plate, and the magnitude of this electric field is equal to the charge per unit area on the plates of the capacitor divided by the constant epsilon naught. Furthermore, recall that the magnitude of the electric field outside the plates of a parallel plate capacitor is equal to 0 newtons per coulomb. Now, using this formula for the strength of the electric field, we can easily calculate the voltage difference between the plates of a parallel plate capacitor. Recall that the voltage difference between 2 points is equal to minus the component of the electric field that's parallel to a displacement times the displacement. Since the electric field lines inside a parallel plate capacitor point horizontally, we can consider a displacement going from the negatively charged plate horizontally over to the positively charged plate. So this is my displacement. If the capacitors are separated by a distance d, then the length of the displacement is just equal to d. And because the displacement points in the opposite direction as the electric field, the component of the electric field that's parallel to the displacement is just going to be equal to minus the magnitude of the electric field. So I see that the voltage difference here is just minus times minus the magnitude of the electric field times the displacement, which is just d. So this is going to be equal to the charge per unit area on the plates of the capacitor divided by epsilon naught times d. Finally, if this plate has an area A, then we can write the charge per unit area on the plate as being equal to the charge on the plate divided by the area of the plate. So I can write the voltage difference is equal to the charge on the plate times the distance between the plates divided by the area of the plates of the capacitor times epsilon naught. So this is a formula for the voltage difference between the plates of a parallel plate capacitor. Now, there's a couple things to notice about this formula, so let me go ahead and write this formula down again. We found that the voltage difference is equal to the charge on the capacitor times this quantity d divided by the area of the plates, epsilon naught. The first thing to notice is that the voltage across the plates of a parallel plate capacitor is proportional to the charge on the plates of the capacitor. The second thing to notice is that this quantity right here that I have shown in parentheses only depends on the capacitor. This depends on the distance between the plates of the capacitor, and it depends on the area of the capacitor. So this describes the capacitor. So what we'd like to do is we would like to take this term right here, which only depends on the properties of the capacitor, and we'd like to call this something. So what we do is we say that the voltage across the plates of a capacitor is equal to the charge on the capacitor divided by this quantity called the capacitance. Since this is equal to, we know that this is going to be equal to Q times D divided by A epsilon naught, we see that the capacitance is equal to the area of the parallel plate capacitor times epsilon naught divided by the distance between the plates of the capacitor. So this is how we calculate the capacitance of a parallel plate capacitor. Now, whenever I introduce this idea of the capacitance of a capacitor, I'm always asked, well, what exactly does the capacitance mean? Like, what does this tell us? And basically, the way to think about the capacitance is the capacitance describes the capacity of the capacitor. In other words, it describes the ability for the capacitor to store charge. So for example, if I rearrange this formula to solve for Q, I see that the charge that we can put on the capacitor is equal to the voltage times the capacitance. So in other words, the capacitance here describes the capacity for the capacitor to hold charge. So the charge on the capacitor is proportional to the capacity, or the capacitance, of the capacitor. Now, of course, I can always add more charge to the capacitor by increasing the voltage as well. So if I push hard enough, I can always add more charge to the capacitor. But for a particular voltage, if I push a particular amount, the capacitance tells me how much how much charge I can store on that capacitor. Now, as always, whenever I introduce a new type of concept like this, I like to take a step back and look at the units of this. So we found that the voltage across the capacitor is equal to the charge on the capacitor divided by its capacitance. And dimensional analysis tells us that the units on both sides of an equal sign have to be equal. So using this, I can solve for the units of the capacitance, and I see that this is going to be equal to the units of charge divided by the units of voltage. So we see that this is going to be equal to coulombs per volt. And this quantity right here, a coulomb per volt, is called a Faraday, which we usually denote with this letter F. And this is named after a famous physicist named Michael Faraday, who invented or discovered the concept of electromagnetic induction. And that's something we're going to talk about a little bit later in the year. Now, because the capacitance of a capacitor increases as we bring the plates of the capacitor closer together, right? Remember that the capacitance of a parallel plate capacitor is equal to epsilon naught times the area of the plates divided by the distance between the two plates. So as I decrease this distance between the plates of the capacitor, the capacitance increases. And so one of the things that we do in practice when we actually build a parallel plate capacitor is that we sandwich a piece of insulator between the two metal plates. So what I'll do is I'll have these two metal plates that are the plates for my capacitor, and then I'll just take like a sheet of paper and I'll sandwich the paper between the plates of the capacitor so that the plates are very, very closely spaced to each other. And this material that we place between the plates of a capacitor is called a dielectric. And typically what we'll actually do is not only will we put a dielectric in between the plates of the capacitor, but we'll also put them on the outsides. And then once we've done all of this, we'll take this whole thing and we'll roll it up. And so we'll create this sort of cylindrical shaped thing. And then you stick this whole thing inside a can. So if you ever open up an electric device, you see this little metal cans that are soldered onto the thing, the circuit board. Those little metal cans are typically capacitors. And the dielectrics, it turns out, play a very important role in a capacitor. One of the things that I haven't really mentioned about capacitors is that it's very difficult to build a capacitor that even has a relatively modest capacitance. Like, for example, like a 1 farad capacitor is very difficult to build. In fact, I think I have a problem in the homework where I ask you to calculate the area of a parallel plate capacitor that has a capacitance of 1 farad. And you'll find that it's just extremely large, like a square mile or something like that. And one of the things that we can do to help make it easier to build capacitors that have larger capacitances is by picking certain materials to put in between the plates of the capacitor. So if you think about this, if we have these two plates that are very closely spaced, the electric field between the two plates is going to be very, very large. So whenever you put any material inside the plates of a parallel plate capacitor, these electric fields will exert forces on the electrons and protons in that material. And what it'll do is it'll actually polarize the atoms. So it'll pull the electrons towards the positively charged plate, leaving the nucleus with a slight positive charge. So all of our atoms now are these little dipoles. And what this does is it actually helps to shield the electric field inside the parallel plate capacitor. So almost like a metal, remember the metals will completely cancel out the electric field inside the parallel plate capacitor. But these dielectrics, they don't completely cancel the electric field, but they get rid of a lot of it. And so what happens is that these surface charges that build up on the dielectric, they reduce the strength of the electric field between the plates of the parallel plate capacitor. And we describe the effect of this using something called the dielectric constant. So we say that the strength of the electric field inside the plates of a parallel plate capacitance is equal to the strength of the electric field that would be there without the dielectric divided by the dielectric constant of the dielectric. And so what this does to the voltage between the parallel plate capacitor, well, the voltage difference, remember, is equal to the strength of the electric field times the distance separating the parallel plate capacitor. And if there's a dielectric, this electric field is equal to the strength of the electric field without the dielectric divided by the dielectric constant. And remember that the strength of the electric field inside a parallel plate capacitor is equal to the charge on the plates of the parallel plate capacitor divided by epsilon naught times the area of the plates. So looking at this, we can see, so this is going to equal Q times D divided by the dielectric constant times epsilon naught times the area. So the capacitance of the parallel plate capacitor is now equal to kappa, that's the dielectric constant, times epsilon naught A divided by D. In other words, it's going to be the dielectric constant times the capacitance of the capacitor without the dielectric constant. So if you stick a dielectric inside a capacitor that has a dielectric constant of 2, then you will double the capacitance of the capacitor. Also, looking at this, we can see that the voltage difference decreases with the capacitance. So actually, this is going to be equal to the voltage difference that would have been there without the without the dielectric divided by the dielectric constant. So this delta V naught, that's the voltage difference that would be across the plates of the parallel plate capacitor without the dielectric. And the C naught here, that's the capacitance of the parallel plate capacitor without the dielectric. So we can see that when we put a dielectric in between the plates of the parallel plate capacitor, it decreases the voltage by dividing it by K, or kappa, and it increases the capacitance by multiplying it by that dielectric constant. So let's go ahead and look at an example. In this example, we're told that a parallel plate capacitor is connected to a 9-volt battery. And after the capacitor is charged, we remove the capacitor from the battery, but we leave the charge on the plates of the capacitor. We then pull the plates of the parallel plate capacitor so that the distance between the two plates is doubled. The question now asks, what is the voltage across this parallel plate capacitor? So let me kind of just draw a little picture of what we have going on here. So we have these two plates of a parallel plate capacitor, and they're going to be hooked up to a battery, and this battery is going to put charge on the parallel plate capacitor. So we're going to have positive charge building up over here, and then negative charge building up over here. Then we're going to remove the battery, so we just have the two plates, and then we're going to pull these two plates apart. So we're going to increase this distance. So we're going to double this distance from D initial to 2 times D initial. So we're going to double that distance. And the question is when we do this, what's the new voltage difference between the plates of the capacitor? So remember that the voltage difference between the plates of a capacitor is equal to the charge on the capacitor divided by the capacitance. And this is also equal to, because the capacitance is equal to epsilon naught times the area divided by the distance between them. So this is going to be equal to Q times the distance between the plates of a capacitor divided by epsilon naught times the area. So looking at this, we can see that the voltage across the parallel plate capacitor is proportional to the distance between the two plates. And since everything else is going to be held constant, we're going to have the same charge on the plates, right? We're not going to change the charge, we're just going to separate the plates. And because the area of the parallel plate capacitor, obviously that's not changing, the only thing that's changing is this distance between the two plates. So if I double this distance, I will double my voltage. So we can see that the final voltage is going to have to be equal to 18 volts. So it's a very simple problem. Another way that we could think about this problem is that, remember that the electric field inside a parallel plate capacitor is equal to the charge per unit area on the plates divided by epsilon naught. Right? So we have this formula here. So since the charge that's on the plates is remaining the same, the strength of the electric field between the parallel plates is going to remain constant, even as we increase the separation between the two plates. And since the voltage difference is just the electric field times the distance, we can see that when we double the distance, we're just going to double the voltage, because the strength of the electric field remains the same. So what I would like to do now, is I want to try to derive a formula for the total potential energy stored on a parallel plate capacitor. And this is actually a pretty complicated calculation to do, and the reason is that if we think about just a metal plate that has a whole bunch of charges on it, remember that the potential energy associated with a collection of charges is equal to the potential energy due to every pair of charges. So I have to add up the potential energy for all the different pairs of charges. And so if I have a very large collection of charges, like I'm going to have on a parallel plate capacitor, this is a very complicated thing to do. It turns out that there is another way that we can calculate the potential energy in a charge distribution like this, and that is by calculating the work that I would have to do to move the particles from out to infinity into their charge distribution, so into the place where they're at. So if we think about this, the first charge that I move, if it starts out here at infinity and I move it into the parallel plate capacitor, it'll be very easy because there's no forces that are opposing me from moving this charge from where it is initially onto the parallel plate capacitor. So I do no work in moving the first charge onto the plate. However, when I try to move the second charge onto the plate, I'm going to have to exert a force on this charge because this particle over here is going to be repelled by the charge that's already on the plate. So I will have to do some work when I move this charge from out to infinity onto the parallel plate capacitor. And this work that I do in moving this charge onto the parallel plate capacitor is going to be equal to the potential energy that is associated with these two charges. So let me call this first charge Q1 and the second charge Q2. So I've calculated now the potential energy associated with this pair. Now if I take a third particle from out to infinity and I move it onto this parallel plate capacitor, I'm going to have to do even more work on this charge, because not only do I have to do work to overcome the repulsive force between this new charge, let's call this Q3, and this charge Q1, but I also have to overcome the repulsive force due to Q3 and Q2. So when I add this third charge on here, the work that I do in adding this is going to give me the potential energies associated with Q2 and Q3 as well as Q1 and Q3. Right? Because the work that I do in overcoming the repulsive force due to Q1 gives me the potential energy between Q1 and Q3, and the work that I do in overcoming the repulsive force due to Q2 gives me the potential energy between Q2 and Q3. So you can see that if I just calculate the work that I do in moving these charges one by one onto the parallel plate capacitor, I end up actually calculating the potential energy for every single pair. So it gives me the same final potential energy to do things that way. So we want to use that same kind of idea to calculate the total energy that's stored on the plates of a parallel plate capacitor. So the idea is that I want to calculate the amount of work that it has to be done to move one charge from one plate of the capacitor over to the other plate of the capacitor. And that first charge that I move from one plate to the other, I don't really have to do any work because these plates are uncharged initially. There's no electric field that I have to overcome when I move the first electron from one plate to the other. However, once I've moved even just one electron from one plate of the capacitor to the other, there is now an electric field that exists between these two plates. So when I move the second electron from one plate to the other, I'm going to have to do some work on the electron to overcome this repulsive force. Similarly, when I add the third electron, I'm going to have to do even more work, and then I'll have to do even more work for the fourth electron. The total energy that's going to be stored on these plates is equal to the sum of the work that I do in moving each and every electron from one plate to the other until I reach my final charge. The work that I do in moving a single electron from one plate to the other is equal to the change in the potential energy, because I'm pushing the electron. The work that I do when I move that electron is a non-conservative force, so it's going to equal the change in the potential energy of the electron when I move it from one plate to the other. So if I move a small charge, we'll call it delta Q, from one end of the capacitor to the other, and if the capacitor has a charge Q already, well, the work that I do in moving that charge delta Q is equal to the charge that I move, delta Q, times the voltage difference between the two plates. That's the energy difference that I'm going to move the electron through, or the charge delta Q. And the voltage difference between the plates of the capacitor, remember that's Q divided by the capacitance of the capacitor. So this is the amount of work, I'm going to call this delta W, the amount of work that I have to do to move a charge delta Q from one plate to the other when the parallel plate capacitor already has a charge Q on it. So the total work that I have to do in moving all of these charges is going to equal the sum of the work that I do in moving each and every charge. So the total work is just going to equal, so I'm going to sum up all of these. So this is going to equal this delta Q times the voltage difference, which is Q divided by C. And the idea here is that this delta Q is going to be extremely small. So whenever I add up something like this, we can treat this as an integral. So we can say that this is approximately equal to the integral, and I'm going to integrate from an initial charge 0 up to a final charge Q, and this is going to be Q divided by C dq. So I'm taking the limit as this delta Q basically goes to 0, and now I'm summing up all these infinitesimal bits starting from 0 and ending with the final charge Q. So if I do this integral, I'm going to see that this is going to be equal to Q squared divided by 2C. So this is the formula for the total energy that's stored on the plates of a parallel plate capacitor. And we'll usually denote this energy with a capital U. That's the same symbol we use to describe the internal energy of a gas. And obviously, because this is a non-calculus based course, you're not going to have to know how to do this derivation. I'm not going to expect you to remember this derivation, but it's just one of those things. I don't like to present a formula like this without showing where it comes from. So now, even if you don't understand calculus, you at least kind of get this concept of what we're doing. So we're moving charges one by one, and we're adding up the energy associated with moving each charge. And that's how we get this formula. So on the previous slide, we found the formula for the total energy that's stored on a parallel plate capacitor in terms of the charge that's on the parallel plate capacitor and the capacitance of the parallel plate capacitor. However, in many situations, we might not know the charge on the capacitor. Instead, we might be given the voltage across the capacitor. For example, I might ask, if I hook up a capacitor to a 9-volt battery, how much energy will be stored on the parallel plate capacitor? So what we can do is we can use the relationship between voltage and capacitance, voltage and charge, to rewrite the formula for the potential energy. So we found the energy stored on the parallel plate capacitor is equal to the total charge on the plates squared divided by 2 times the capacitance of the capacitor. So if I rearrange this formula, V is equal to Q divided by C, to solve for the charge of the capacitor, I see the charge on the capacitor is equal to the voltage times the capacitance. And if I plug that into this formula up here, so I have Vc quantity squared divided by 2C, I'm going to see that this is going to equal 1/2. One of my capacitors and the capacitances in the numerator will cancel with the capacitance in the denominator, so I'll have 1/2 C V squared. So this is another way that I could write the total energy that's stored inside a parallel plate capacitor in terms of the capacitance and the voltage. Similarly, I might want to write the internal energy stored inside a capacitor in terms of the charge on the capacitor and the voltage across the capacitor. So if I do that, in the previous slide we found the internal energy is equal to 1/2 C V squared. We also know that the voltage across a capacitor is equal to Q divided by C. So if I try to solve for C to get rid of the capacitance, I could rewrite this as C is equal to Q divided by V. And if I plug that into this formula here, I see that the internal energy is going to equal 1/2 Q divided by V times V squared. Or in other words, it's 1/2 Q times V. So this is just another way that we could write the total energy that's stored on the plates of a parallel plate capacitor. So altogether, there are 3 different formulas that we can use to calculate the energy that's stored on a parallel plate capacitor. Now, before you start thinking that this is a whole lot of formulas to remember, keep in mind that we really only need to know one formula and the relationship between voltage, charge, and capacitance. So if you know these 2 formulas, you can derive these other 2. You just need to know the energy that's stored on a parallel plate capacitor, as well as the formula for the voltage across a parallel plate capacitor. So at this point, I think I'm going to end the discussion of capacitors. And in the next video, we're going to start discussing circuits. So we'll start talking about resistors, and we'll also see how capacitors are actually used inside a circuit.